Motion in a magnetic field. We will now consider in greater detail the motion of a charge moving in a magnetic field. We have learnt in mechanics that a force on a particle does work if the force has a component along or opposed to the direction of motion of the particle. In the case of motion of a charge in a magnetic field, the magnetic force is perpendicular to the velocity of the particle. So no work is done and no change in the magnitude of the velocity is produced, though the direction of momentum may be changed. We shall consider motion of a charged particle in a uniform magnetic field. First, consider the case of V bar perpendicular to B bar. The perpendicular force QV bar cross B bar acts as a centripetal force and produces a circular motion perpendicular to the magnetic field. The particle will describe a circle if V bar and B bar are perpendicular to each other. If velocity has a component along B bar, this component remains unchanged as the motion along the magnetic field will not be affected by the magnetic field. The motion in a plane perpendicular to B bar is as before a circular one, thereby producing a helical motion. If r is the radius of the circular path of a particle, then a force of mv square by r acts perpendicular to the path towards the center of the circle and is called the centripetal force. If the velocity v bar is perpendicular to the magnetic field B bar, the magnetic force is perpendicular to both V bar and B bar and acts like a centripetal force. It has a magnitude QVB, equating the two expressions for centripetal force. mv square by r equals to QVB, which gives r equals to mv by qb for the radius of the circle described by the charged particle. The larger the momentum, the larger is the radius and bigger the circle described. If omega is the angular frequency, then V equals to omega r. So omega equals to 2 pi V equals to QB by m, which is independent of the velocity or energy. Here, V is the frequency of rotation. The independence of V from energy has important application in the design of a cyclotron. The time taken for one revolution is t equals to 2 pi by omega is nearer to 1 by v. If there is a component of the velocity parallel to the magnetic field denoted by v2, it will make the particle move along the field and the path of the particle would be a helical one. The distance moved along the magnetic field in one rotation is called pitch p. Using equation, we have p equals to v2t equals to 2 pi m v2 by qb. The radius of the circular component of motion is called the radius of the helix.